Okay, today we're going to talk about the potential from various charge arrangements, and we'll start with the dipole since that's one of the most simple arrangements. Okay, so as you know, as we've talked about, the voltage is going to simply be K sum of Q sub I over R sub I as I ranges from 1 to n. There are only two charges in this. There's a positive Q and a negative Q, both of the same magnitude. So basically it's going to be K times Q1 over R1 minus Q2 over R2. I'll put a plus for now. And then basically, since both Q's are the same, this Q is the same as that Q. The only difference is a minus, right? So you could just basically pull out a Q like this, and those numerators both become 1s. And we don't even have to call it a Q1 or a Q2. We'll just call it a Q. And then the middle sign is going to be negative right in here. So if you don't believe me, you can redistribute it. You get Q over R1 minus Q over R2. Okay. Now when I say R1, I'm referring to this distance between the positive charge and the point P. And when I say R2, I'm referring to the distance between the negative charge and point P. Okay? So the book likes to call these R plus and R minus, which I think is an okay way to do it. You know, it just means the distance to the positive, that's R plus, and the distance to the negative, that's R minus. So I'm going to go ahead and use that. But that's a real simple arrangement of charge because it's only two charges. Okay, notice that R1 and R2 are not the same, or R plus and R minus are not the same. In fact, R plus is slightly shorter than R minus is. Okay, so the first thing I'm going to do is find a common denominator for these two fractions. So your common denominator is going to be the product here. So you're going to times the first one top and bottom by R minus and multiply the second one top and bottom by R plus. Okay, so we get this rather awkward statement that the total potential in this situation is KQ times R minus minus R plus all over R plus times R minus, like that. Okay, so that's going to be our formula there that we kind of springboard off of. Okay, and now in this diagram, this is a little bit hard to convince people of, but you'll notice that there are no right triangles anywhere, right? There's no right triangles anywhere. So that makes it pretty awkward, and nobody likes using law of cosines. Also, the angle that we usually use for theta is measured from the center of the dipole. So you can see there's this theta here at the center, but it's not really connected to either of our blue segments. So that's kind of annoying. But here's the cool thing. Most of the time when we study a dipole, we stand back from very, very far away. In other words, the charge to charge distance on a dipole, in nature anyway, is terribly small. I mean, really, really, really small. The D there is tiny, usually, nanometers or whatever. So we measure them from an inch away, if that makes sense. So the distance R is usually much, much greater than D. And if we allow R to be much, much greater than D, things simplify quite a bit. Okay, so the first thing that will happen, so basically most dipoles are that's a typo. Most dipoles are studied from a distance that is much larger than D. Okay, so one of the things we can do is we could say, look, D cosine theta is pretty much the same thing as R plus minus R minus. Okay, this is a little bit hard to show, but in the diagram, we're kind of treating these two tilted segments as collapsed together. So imagine taking these two tilted segments like this and just kind of swinging them together. So now it looks like this, right? But remember, it was back in the original picture, the R minus was a little longer, right? It's a little longer, so it actually looked more like this when they swing together. Okay, so this was R plus, this is R minus, and then this distance right here would be the difference. R plus minus r minus. Okay, so that little distance right there, if you kind of go back to your diagram, you'll see there's a little green right triangle right there. And this is just an approximation. But we could treat d cos theta as that same distance right there. So I'm going to go back to this picture now. Originally, it looks like this. We have a short segment and a long segment. Theta is actually measured from the middle, like this. So another thing we could do is kind of just move that theta to the bottom, right here, because it's not going to make much difference when you move it. You're not moving it very far, so the theta wouldn't change much. And then this little green right triangle, cos theta, is going to be adjacent over d. In other words, adjacent is pretty much the same thing as d cos theta. It's not exact, but it's a pretty good approximation. And the adjacent side there is the difference between R1 and R2, as I drew a minute ago when I drew this picture. So the adjacent is actually right here. It's this thing, R plus minus R minus. I'm sorry, it's R. Technically, it's R minus R plus, right? The longer one minus the shorter one. Yes, R minus R plus. Mr. Shore should have written R minus R plus. So that's a little bit hard to show, but this avoids having to do limits. We don't really want to work with limits here. Just trying to think more or less just approximation-wise. Okay. Also, R plus times R minus, since R plus and R minus are these two blue segments, since when you're really far away, the difference between them is quite negligible. If you're really far away, you don't study the differences in these. You would say that I said that wrong. Mr. Short said that wrong. If you're studying them from far away, they're approximately equal. For example, when you measure the distance from here to two stars, and one's like a few hundred miles further from the Earth than the other one is, you don't really care, right? You're going to be measuring in astronomical units. Nobody cares if there's a discrepancy of a few hundred miles. So what I'm saying is, even though R1 and R2 are different, R plus and R minus are different, the product isn't much different from just squaring R. Okay, so R is that one down the middle. So we're saying that if you take R plus and R minus and you times them together, that's not too different from just squaring R, if that makes sense. Okay, so sometimes physicists do stuff like this, and it's, you kind of wish they'd just do the calculus way and just do limit. Just do limit. What happens in a limit when R minus approaches R plus or something? But they don't do that. They just kind of play around with it. Okay, so now the fraction's so much simpler. We're going to look back at this one. This is what we were going to springboard off of, the big yellow one at the top. We're saying that numerator in that fraction is approximately the same as d cos theta. And the denominator is approximately the same as r squared. Okay? So all that just to say that. Also, you might remember that if you see a QD, he's such a cutie, you're supposed to replace it with P, the dipole moment. It's been a while since we've said that, but that is still true. And I do see a QD floating around in my work here. There's a little QD right there. See him? So how about we write V then in terms of dipole moment, Kp cos theta over r squared. Okay, so whenever I do a two arrangement charge, I feel like I'm actually studying a problem that's more complicated than like a ring of charge. Ring of charge always feels easier to me. But that was a lot of approximating to come up with that. Okay? All right, and then down at the bottom, we also include one more little drawing of P, because we haven't seen P in a while. P points from the negative charge to the positive charge. Let me clear the ink here. So you probably remember this little guy, vector P. He points from the negative to the positive along that axis. So how long depends on how big the charge is and how big the displacement is. Okay, now there's a little note at the bottom too. This is something I was reading about, and I thought this is interesting. I should mention it now because this might be one of the last chances to talk about dipoles for a while. some molecules like water have a permanent electric dipole. So you might remember how the hydrogen stack up with the oxygen. There's a 105-degree angle between these. You should have also seen that in your biology class and your chem class. Okay? So what happens is, if you just draw a line down the middle, right, like this, you end up with more, it's almost more or less like a dipole. So the oxygen is the negative, the hydrogen is the positive. So it's kind of like a dipole. And it's a permanent situation. Like, we can't really change that angle, that 105-degree angle. Okay, so that's sort of a permanent electric dipole found right there in nature. Now, this is an interesting thing, and you probably know this from van der Waals forces and studying this in chemistry and stuff, but some molecules can have their center of positive charge and their center of negative charge temporarily displaced by an external electric field. In other words, you can actually induce a dipole moment on a molecule that normally wouldn't have one. So for example, let's say you have a molecule and everything's actually you could really do this with I don't know what I want to draw. Let's say you have some situation where you have this is not even a molecule. This is just like Mr. Shore's creation here. Let's say you have some positive charges and they're stuck together here somehow. They're somehow held together. Okay? And then around this you have a field of electrons orbiting. Okay? So right now the center of charge for the plus is the center of the drawing. So this is, I'm going to call this the center of the positive charges. And the center of the negative charges coincides perfectly with the center of positive charges because the electrons are also orbiting. And so the center of charge for the negatives is the same place. Now, if you stick an electric field on here, or if you set up two plates and you kind of surprise this charge arrangement, what's going to happen to the minuses? They're going to move to the left, right? The blue cloud is going to move to the left, and the red cloud is going to move to the right. So what happens is you get a temporary displacement in their charge centers. So it would look like this now. Here's positive plate, negative plate, and the blues are kind of leaning over here more. They're like more probable to be in their orbits on the left. Remember, orbitals are all probability driven, right? So you get a cluster of negative probability on the left, or I mean negative charge location probability towards the left, and the pluses are being kind of pulled over to the right. So this shifts the center of charge, and it creates actually a dipole. For just the time that the field is there is a dipole going on, and this blue-red cloud thingy is actually a dipole temporarily, with a slight dipole moment pointing this way to the right from negative to positive. So I don't know if you can see that, but we could actually polarize this by shifting the centers of charge away from each other. Okay, now we're going to move on to the fun stuff, and I think the easier stuff. Since total potential is sigma, oh, and Mr. Shore forgot his K out front. It's K times the sum of charge over distance. If we have a continuous distribution of charge, we could use integration to sum up the individual potentials more efficiently. Now, I wrote a little note here saying that technically it is impossible to have a continuous distribution of charge. Okay, so we've talked about continuous distribution of charge, but I'm going to say today that actually that isn't even possible. So I'm going to pause the recording and maybe you guys can tell me why I'm saying that. Okay, so we had a good discussion. We said that electrons cannot be infinitely close together, therefore we can't have a continuous charge distribution. We also said that electrons come in bite-sized pieces, electron charges come in bite-sized amounts, so you can't have them just half amounts or whatever. So everything's real chunky when it comes to real space and real time and everything, as far as we know. Okay, so we would like to now write V total equals K integral of dq over r instead of using the sigma notation. And you'll notice that we're always going to be integrating from some initials to some final amount. So that's the way these integrals are. They're always definite integrals. So there's like an A and a B here from your calculus class. But we're just going to assume that v sub initial is 0. So we're just going to make this assumption, and that way the left side doesn't have to be v final minus v initial. We can just toss out the v initial. We already talked about that last week too. Okay, now let's try our first integral and see if we can get the potential on a charged rod with a fixed length L. This is the hardest one we're going to do today by far. So actually, you might want to write really small. Okay, so imagine a rod of charge, and it has length L, and we're going to cut it somewhere because we want to study an arbitrary point. So Mr. Shore is going to be studying this point P up here, a distance y above the rod. I do not want to necessarily center it above the rod. By the way, the rod is not an infinitely long rod. It is actually a length L rod, as it says. So we're not doing the infinite line of charge. We're doing something brand new. I'd like to put this point off center on purpose, and I'm going to put it a units away from the left endpoint like this. So that little distance will be a. Let me redraw that real quick. All right, so the left distance is a, and since the total rod's length is L, the other piece will just be L minus a. Kind of reminds us of what we were doing in calculus this morning with optimization. So that was a pretty sloppy drawing. I was going to impale this thing with an xy axis anyway. So what Mr. Shore was going to do is make sure that point P is nicely on the y-axis. And then I was going to put the rod off center like this. And since the part to the left of x equals 0 is a units long, I'll just label this point x equals negative a. And since the other part on the right is L minus a units long, it'll have a positive x coordinate L minus a. Okay, so the reason I'm drawing this on an xy axis is because eventually I'm going to integrate, and when I integrate, I'm going to want to measure things and how far I'm going and you know which piece I'm studying and all that, and so it makes sense to have a ruler of sorts here. The y-axis is not going to do much in this problem. Now, if you just pick a sample chunk of charge, say this one, it is a certain distance r from our point that we're interested in, like that. So we'll be studying the little red chunk of charge. There's lots of things I could label that chunk. I could label it dq. I could label it dx. It depends on how you want to think. Its width is dx. The amount of charge it contains is dq. And by the way, this is a uniform distribution of charge across here. So I forgot to mention uniform lambda. Okay? So I could call it dx, dq, or how about this? Just dq equals lambda dx. So that implies that its width is dx and its total charge in that little slice is dq. And I've related them. So this is dx wide. It is also dq charge. And the relationship is in the box right here. Okay, so that's good to have handy. Also, for just geometric considerations, we will be changing this distance down here, the green arrow. So we'll just call that distance x. But the y value, the distance up to point P, will never change. It'll never change. So I'm just going to call that y. I didn't want to use L because I already used L. I didn't want to use D because the calculus has dx and stuff all over the place. I thought the D might look weird. So I'm just using y. So y is fixed, but x is variable. And r then is the distance diagonally from our point of study to our charge configuration. So r will always be measured from the point you're studying to the charge that you're studying, Okay, always. Okay, so here's where we have to kind of sum things up. Oops, sorry about that. So the integral that we wrote up above is a universal rule. It's just k integral dq over r. And there's no vector signs, no r hats, nothing. It's scalar potential. So that's good news. The dq we said we can write as lambda dx. And it would be nice to pull the lambda out if we believe it's constant, and it is, no matter where you are on the x The lambda never changes, so let's pull out the lambda. So now we have a k lambda out front. And it would be also nice if that denominator was an r. I'm sorry. It'd be nice if the numerator was a dr, or if the denominator was like x related. So let's use the Pythagorean theorem to rewrite r real quick. R squared should be x squared plus y squared. So r is the square root of x squared plus y squared. And now we run into an integral that we've never solved before. We didn't solve it in any class at any time. It is not a u sub integral. It is not an arc trig function. It is just plain none of it. So what we're going to do is we're going to u sub this thing until it's familiar looking. And we're also going to use a very sneaky trick. Okay? All right, I need more space, so Mr. Shore is going to erase everything I wrote above it and move that thing up to the top and make that my center of focus. So I have k lambda integral dx over square root x squared plus y squared. All right. Now, here's the tricky part. We're going to let y, I said that wrong. We're going to let x be y tangent theta. We're going to let x equal y tan theta. Let's see what that does. K lambda integral dx over square root, and then we have y squared tan squared plus y squared. Can you see why this was not a bad choice? Hold on one second. Let me record. Pause. Okay, so good. A student noticed that we're going to get a tan squared plus 1 here in a moment, which is really sec squared. So it's going to be like this. First, we're going to pull out that y that's on the bottom. And tan squared plus 1 is sec squared. So we end up square rooting that. We just get sec theta. That just feels like progress to me. Okay, now what about dx? We can't have theta and x in the same problem. Well, remember something that we didn't do a minute ago. When you write down a u sub, the first thing you do is write down what you want your variables to change into. But you're also supposed to find the derivative of that. It's been a long time since we've done any kind of substitution. But if you've replaced your x, you've really also replaced your dx. So Mr. Shore is going to write dx. We haven't done this in a long time. If x is y tan theta, then dx is y sec squared theta d theta. So what I did there was I basically found the y is a constant, remember? Y is fixed. I just basically found the derivative of tan theta. It's sec squared theta d theta. So now I'm going to go in and replace the numerator dx with y sec squared theta d theta. Y sec squared theta d theta. That's the numerator there. And y sec squared theta d theta. That's the numerator on that step. Hopefully you're using pencil so you can just erase. Otherwise you kind of have to rewrite it a bit. And lastly, y sec squared theta d theta here. Ooh, this is really cleaning up. Okay, first thing that happens is the y that we had on the bottom from earlier, we pulled it out of the radical, cancels with the y that was in the top. Okay, that's the first cancel. Then one of the powers of secant cancels out. Okay, so now Mr. Shore is going to go back to the top here, and this will become my new focus. Now I have this integral to work on. K lambda, literally integral of sec theta d theta. Man, that feels like progress. Here's the problem. We've never done that integral either. Student asked about the limits of integration. We are going to be going from x equals negative a to x equals L minus a. But I'm going to change everything back to x before we hit that phase. So I was just leaving off the limits. Here on my paper, I just kind of did a little squiggly throughout my work. I just drew a little squiggly here. So I didn't have to keep copying them over and over and over. Okay, now, how do you integrate sec theta? Oh, well, you multiply top and bottom by sec theta plus tan theta. Okay, so it's magic. Watch this. You might have seen this trick in BC Calc if you were studying hard enough. There were plenty of websites that would teach you this trick. You times top and bottom by sec theta plus tan theta. Oh, I don't know why I put that on the bottom. Our secant theta was on top. I'll put it in the front. So Mr. Shore is, we had a sec theta there all by his lonesome self. We're going to times by sec theta plus tan theta over sec theta plus tan theta. You might say, what the heck does that accomplish? Well, now the top is sec squared theta plus sec tan. And the bottom is sec plus tan. Look at the numerator. Both of those terms on top should look very, very familiar. Where have we seen sec squared? What is sec squared? The derivative of tangent. Good. And where have we seen sectan? The derivative of secant. In other words, that's du over u. If u is sec plus tan, what would the derivative be? It would be sectan plus sec squared d theta, which is our numerator. Whew. Okay, now I'm going to go back to the top again. That was like a magic trick, right? And now our integral literally looks like this. K lambda, integral of du over u. And finally, ln, absolute value u. Now, we've got some limits of integration to apply, but we are far from home, Toto. Okay, so recall that u was sec theta plus tan theta. So let's go and write that down again. Let's see here. We're trying to get this back to where we were before. U was sec theta plus tan theta. Let's see. What the heck was theta anyway? Oh, I remember. We had this little rule that we were going to change x to y tan theta. I remember that. Oh, yeah. That can be drawn as a picture. So if you just draw a right triangle with a theta in it, opposite over hypotenuse is x over y. So it would be this triangle right here. Opposite over hypotenuse is x over y. The hypotenuse would be the square root of x squared plus y squared. And now we could rewrite the u in terms of all x's. So since u is sec theta plus tan theta, in our drawing, sec theta would be hypotenuse over adjacent, and tangent would be opposite over adjacent. So in other words, it's going to look like this. It's going to be square root of x squared plus y squared over y plus x over y. That's u. Oh, I probably erased that too soon. I'm so sorry. I'm going to redraw that real quick. We had x equals y tan theta. I was thinking of that as x over y equals tan. And then I was thinking of a right triangle where this is theta, this is x, this is y, and this would have to be Pythagorean Theorem. And then I figured out that sec theta would be that first fraction, x squared plus y squared square root over y. And then x over y would be the tan there. Wow. Okay, we got our integral now our answer in terms of x's and y's, but we haven't plugged in our limits of integration yet. So here's what we have. we have total potential equals k lambda, and then there's an ln absolute value u. So it looks like this, x squared plus y squared plus x, and I'm just going to put it all over y. I still have to plug in negative a and L minus A, my left and right endpoints. And then I'll subtract, you know. I'll leave that down at the bottom. Okay, so I have this, K lambda, Ln, I'm going to plug in the L minus A. So I get square root of L minus A squared plus y squared plus L minus A all over y minus ln square root of a squared plus y squared plus negative a all over y and what happens when you subtract two logarithms? When you subtract a logarithm minus a logarithm, so you have ln m minus ln n, what happens? You could just put m over n, right? You could just put them together into one. So that's the cool thing about integrating and getting a log is you could actually take your capital F of it, like your limits of integration, plug them in, you're subtracting, then you recombine them into a log anyway. Okay, so I'm going to use that rule now. I'm going to put these back together. So now it looks like this. K lambda ln, and then on the top I have square root of L minus A squared plus y squared plus L minus A over y. And this is all over square root of A squared plus y squared plus negative A. So basically just minus A. Oh, that eraser tool is so awkward. It erases too much stuff. Let me rewrite that. At least I didn't lose my cool top fraction. This is supposed to be all over square root of A squared plus y squared plus negative A all over y. And then the y's cancel out here. And this is the answer. Okay, so I'm going to write my answer in a box at the top. And I wish I'd given you 2 full sheets of paper for that. I'm so sorry I gave you so little space. Here's our final answer. If you have a rod of length L and you want to study at any point in space the potential, we have real nice symmetric answer actually. It's not a terrible looking answer. The top and bottom look very similar here. Okay, now the book doesn't do this problem. The book thinks this is a little ambitious, but I had a feeling that we should eventually do something like this because everything we've done is so darn symmetric. I just felt guilty, like I wasn't going to really show you the real formulas, you know? But you can see why the book would probably like to leave this alone and leave this out. So what they do is they actually fix the point P directly above the left endpoint of the rod. So I'll show you what they do. So they basically, they go like this. Here's the rod. And when they pick their point P, they insist that it has to be directly above the left endpoint. You know what I'm saying? So in other words, what are they making 0? In my drawing, I have this A here, right? In my drawing, I included that I included some of the rod on the left, and this distance was A from here to here. So what are they really doing? They're making A equal to what? 0. Okay, so let's look at some special cases real quick. Let's let A equal 0. In other words, the point is directly above the left endpoint of the rod. Now, if you make A 0, you do get a simpler formula. You get K lambda ln square root of L squared plus y squared plus L all over just simply y. And this is the book answer. But I wasn't satisfied with that because I thought, Well, what if what if the point isn't directly above the left endpoint of the rod? You see what I'm saying? And why the heck would it be anyway? Like, who says it has to be over on the left? Okay, so our answer reduces to the book answer if we are careful to plug in a equals 0. What else might be a nice place to put point A? This is very important what we're doing right now, so don't tune me out, guys. I know you're tired. I'm tired too. You probably slept a little less than I did, but I didn't sleep that much either. Where else might we want to put the green dot? Besides above the left endpoint, where else might we want to put it? So much for the case where A is 0. Let's try another special case. Somebody suggested we make A equal to what? If this is the length of the rod, and then we want A to be the left piece and the right piece to be L minus A. If we want to stick right to the middle of the rod and go right above it and measure the potential, then A would be just half of L. So let's let A be half of L and see what happens. So A equals L over 2. That's sort of another special case where it's right smack in the middle. Okay, so then the vector, the voltage would be K lambda Ln. Oh, and I realize these are supposed to be absolute values, not brackets, right? Although L minus A is positive, Y is positive, square root of that's positive, L minus A is positive. In other words, you're not going to get any negatives anyway. I'm not even sure they're necessary, but technically, algebraically, they are absolute values. Okay, so let's see. If I make A equal to L over 2, ooh, that's going to be weird. This is going to be half L, and you're going to square it. So that's going to be an L squared over 4 right there in the highlighted green. So that's going to be square root of L squared over 4 plus Y squared. And then the Y minus A, L minus A is just going to be L minus half L. So it's just going to be 1/2 L. And then the bottom is just going to be square root of, again, L squared over 4 plus Y squared minus L over 2. So actually, I love the answer. The answer is so cool. And I would expect this beautifully symmetric answer. Look at this answer. The top and the bottom are conjugates. It's beautiful. It's more beautiful than what I started with. So that's the case where A is L over 2. Okay? What was the other suggestion? Maybe just make Y 0. Just let's bring this guy. Maybe we can't put him above the rod, but you know, the first formula I gave you guys, he can be anywhere above the rod. Let's bring him down to the rod. Let's see what happens. We might have a problem here if we do that. Let's see what happens to the potential. So what happens if Y approaches 0? Bring the guy down, right? We get to keep all this green here. Let's just fill it in with new stuff. So if Y approaches 0, then we just basically get square root of L minus A squared plus L minus A all over square root of A squared minus A. In other words, there is no Y. There's no Y's anywhere because Y is approaching 0. And can you see why this gives us an issue? We get 0 on the bottom here. What does that mean? The closer you get to the rod, the larger the potential. And if you land yourself right on the rod, you have an infinite potential. Okay? So we just wouldn't really do that. But we learned something from doing that, playing around with it. Notice on that problem, we didn't have to really take any shortcuts like, let's study it from far away or whatever. That was a legit problem. I want to say something about this answer. We said, and this is all we had time for today. I'm sorry. We are not going to have time for the other simpler ones after this one. I want to say a couple things. First of all, this thing's messy partly because we moved away from the center. But even if we had done it from the center in the first place, it would have been pretty hard. And the reason is, in this problem, the charges don't surround anything. You know what I mean? There isn't any real symmetry, at least from where we're studying. We're up here studying from above. So we don't get that benefit of charge symmetry. Okay, that's one reason. The other reason this is kind of complicated is because of the ln, and the integration just turned out to be awkward. That Pythagorean theorem really messed us up. Okay? Do you remember we said, though, that E is the opposite of the gradient of V? So we could easily turn this back into an E field. Now, how come Mr. Shore didn't do this problem back when we were doing E field? This problem would have been an absolute nightmare. This was bad, but it was a lot worse to do the E field of a finite rod. We can actually get the E field of the finite rod by applying a vector gradient to our answer. So if we basically grad this sucker and throw a negative on here, we get the E for free. When you grad, listen, when you grad, there are at least 4 different coordinate systems you can choose. You can choose x, y, z. You can choose r theta z, called cylindrical. You could choose rho theta phi, which is spherical, or you could choose elliptic coordinates, which we never even learned. In other words, from here, from this scalar answer that we had in blue, we can jump into the vector world through a simple gradient. Then we can times by charge to get force. In other words, we are just a few steps away from finding the E field and a few steps away from finding forces and studying motion. But you can see why vectors are hard to work with from the past. And in a non-symmetric situation like this, potential was the way to go. Okay, so I'm going to stop here today. I hope that wasn't too overwhelming.